In May 1997, IBM's Deep Blue supercomputer defeated reigning world chess champion Garry Kasparov. The press and the public interpreted this six-game match as the ultimate proof that artificial intelligence had finally arrived. This chart visualizes the mathematical scale of a chess game, defined by the Shannon number. There are approximately 10 to the 120th power possible game variations, a search space so massive that navigating it requires enormous computational brute force. Yet John McCarthy, the Stanford researcher who literally coined the term artificial intelligence 4 decades earlier, was entirely unimpressed by the victory. McCarthy argued that Deep Blue was merely a fast fruit fly. Rather than exhibiting true cognition, the machine was operating as a hyper-fast calculator executing predefined heuristics. Chess has absolute boundaries and perfect information. Mastering such a perfectly contained, rule-bound system reveals nothing about a machine's capacity to adapt to real-world ambiguity. The 1997 milestone offered a deceptive illusion of intelligence, masking a deep architectural limitation. Machine intelligence became trapped in this rigid, rule-based paradigm because of a deliberate political fracture initiated in the summer of 1955. This timeline shows how the early pursuit of thinking machines split into 2 diverging paths: Norbert Wiener's probabilistic, interdisciplinary field of cybernetics and John McCarthy's strict, digital approach called symbolic AI. To understand the architecture of modern machine learning, we must track how the original cybernetic path was intentionally starved of funding and academic focus. The technological foundation of artificial intelligence is the product of an academic turf war rather than an objective evolution of computer science. Before 1955, the academic landscape surrounding artificial minds was dominated by cybernetics and automata theory. Norbert Wiener theorized that intelligence was inherently interdisciplinary, relying heavily on analog feedback loops and the synchronous coordination of physical systems. Claude Shannon translated Wiener's theories into physical hardware in 1950, constructing a robotic entity known as the Theseus mouse. Theseus operated on raw mechanical hardware. Below the surface of its maze, an array of telephone relay switches recorded every decision point, while a bar magnet pulled the copper-whiskered mouse through the corridors. The mouse explores the maze dynamically, bumping into walls without pre-programmed rules. After reaching the target, it resets and executes a direct path to the goal. When the maze alters, it updates its internal state, applying fresh trial-and-error exploration to map the new territory. Theseus proved that physical machines could adapt to chaotic environments by observing results and updating their knowledge. This established the exact functional foundation for modern reinforcement learning, 70 years early. John McCarthy viewed analog feedback as a misguided approach. He specifically wanted to escape the multidisciplinary complexity of Norbert Wiener's influence. In his 1955 proposal for the Dartmouth Summer Research Project, McCarthy coined a brand new term, artificial intelligence. He selected this phrasing specifically to avoid the word cybernetics and to exclude cyberneticists from the gathering. Dartmouth established a strict boundary for the newly named field. AI would focus exclusively on digital computing solutions and symbolic logic to perform human-like tasks. The immediate impact of this rebranding was severe. The pioneers of probabilistic learning, early neural nets, and information theory were successfully pushed out of the mainstream academic narrative. The Dartmouth workshop actively constrained the architectural trajectory of machine intelligence. By shutting out alternative frameworks, it blinded researchers to the potential of probabilistic models for decades. The ultimate realization of McCarthy's symbolic paradigm arrived in 1956 with The Logic Theorist, a computer program written by Alan Newell, Herbert Simon, and Cliff Shaw. Its operational objective was algorithmically proving mathematical theorems drawn directly from Russell and Whitehead's Principia Mathematica. The program's architecture passes data between working memory, storage memory, and abstract syntax trees. It parses a logical expression into an inverted tree structure. Distinct methods like substitution and chaining forward act directly on the tree, swapping variables to reach a proven state. This architecture introduced the core philosophy of reasoning as search. However, the mathematical reality of this approach is that the search tree of possible deductions grows exponentially. To prevent the system from getting bogged down in endless calculations, Newell and Simon introduced heuristics. These were hard-coded rules of thumb designed to artificially trim dead-end pathways. The rigid, rule-bound elegance of the logic theorist stood in direct opposition to the messy, probabilistic adaptability of Shannon's Theseus. Yet this brittle, heuristic-heavy architecture became the industry standard. Throughout the 1960s and 1970s, the symbolic logic paradigm completely monopolized research grants and government funding. But symbolic AI possessed a structural flaw, an absolute inability to process real-world ambiguity, statistical uncertainty, and the chaotic nuances of natural language. As the limitations of these rigid systems became obvious, investment collapsed. This triggered the severe funding droughts known historically as the AI winters of 1974 and 1987. Any system built entirely on fixed axioms and hard-coded heuristics will inevitably hit a technological ceiling the moment it encounters the unstructured chaos of reality. The eventual revival of artificial neural networks and the optimization of the backpropagation algorithm in the 1980s and 2000s marked a direct return to probabilistic models. The architecture powering modern large language models relies on statistical data structures championed by Claude Shannon, bypassing the rigid symbolic logic enforced by McCarthy. This lineage is openly recognized within the industry today. Anthropic specifically named their premier language model Claude as a direct tribute to Shannon's legacy. True machine adaptability was not achieved by accelerating the symbolic computing paradigm of 1956. It was achieved by finally resurrecting the cybernetic chaos of 1950.